First of all, gosh, does this contraption work? Yes. Wow, I feel like a cyborg. So many apologies for the lateness of this talk. It's one of the few times it was not my fault. But it's a tremendous pleasure to be here. And I've been asked to give a talk reviewing what's going on with understanding scattering amplitudes recently. Even by the standards of this business, which has been pretty exciting for the last number of years, the last year has been particularly exciting. There's been a flurry of activity in both computing and understanding, and it's a two-way street, the properties of scattering amplitudes. And there are so many things that have happened just in the past year that I won't even be able to mention all of them. So this really won't be a typical review talk in that sense. Let me just start by telling you some of the highlights, just in case you've missed some of these things. And these are just a few of the highlights of things I personally found interesting. And I'll divide them in sort of three categories. First, there have been just some examples of just breathtaking computations that at least I wouldn't have possibly imagined anyone being able to do 5 years ago that people now do like it's nothing. Well, not like it's nothing, but they can do it anyway. For instance, there's a paper that started exploring the multi-regi limit of scattering amplitudes in planar n equals 4 super Yang-Mills that just gave the answer to 10 loops in the first paper. And then soon thereafter it was done to all loop order. Okay? There was the work that you heard about here from Mike Douglas showing that 60 super Yang-Mills diverges at 6 loops. I mean, the fact that you can ask this question and just go do the calculation and settle it is just amazing. And also, there continues to be remarkable progress in at least calculating multi-loop gravity amplitudes, now in theories with less supersymmetry, where there is some indication of perhaps surprisingly good behavior, even with less supersymmetry than maximal, although as usual in this business it's not obvious what surprising really means. So people start exploring and seeing whether the results are indeed surprising or can be understood from some other way. But anyway, the very fact that we can do these calculations at 3 loops and less than maximal supersymmetric theories is just remarkable. So those are just examples of some tour de force computations. There have been at least 2, I think, real breakthroughs, both of which were talked about yesterday. So given that I'm not introducing those talks, I can say less about them, but I'll just mention because they are very important. First, there was the work that Pedro talked about, which is, I think, a real breakthrough in using integrability techniques to calculate scattering amplitudes at finite coupling. And then there's a I think, conceptual breakthrough in formulating n equals 8 supergravity as a novel sort of string theory in twistor space that David Skinner talked about. And these are both things that for many, many years, people wanted to do something like this, and finally, within a few months of each other, they were both done. So since, and of course, there's a huge amount to do following these things up. So anyway, that's just, and finally, people are starting to expose and see in gauge theories, especially in gravity a lot, there's a huge amount of theoretical data that you can dig into and try to understand from some other point of view and try to see what structures are lurking therein. Similar data is starting to be generated also for perturbative string theory amplitudes. So that was, I think, another thing which has really started taking off in the last year, are beginning to expose rich structures in string perturbation theory. For example, a little more than a year ago, tree amplitudes for all n, there are expressions for them, and people can control them. Being able to do that for gauge theory was a major breakthrough that allowed people to discover lots of deep structures in gauge amplitudes, and that data is now available in for at least for gluons scattering at tree level in string theory. There's this completely crazy sounding proposal, which I don't understand at all, but it's fascinating, that relates 2 things that should not be related to each other at all, which is Yang-Mills string theory amplitudes to supergravity amplitudes, okay? Field theory supergravity amplitudes. And Stieberger and Taylor wrote this paper showing that Yang-Mills string amplitudes are the Mellin transform of supergravity field theory amplitudes. This is a crazy connection. I have no idea why it's true. I don't think they have any idea why it's true. Sorry, Stiebiger and Taylor. Maybe you do. But it's certainly not morally obvious why it's true at all. Maybe it's very deep. Maybe it's a coincidence. It isn't obvious, but it's definitely fascinating. And finally, people are also starting to expose this remarkable pattern that's been seen in many, many places. It's been seen long ago in the structure of beta function coefficients in even 5-4 theory. This funny pattern of zeta values and multi-zeta values that make an appearance in computations of coefficients in the renormalization group equation. It's been seen in scattering amplitudes in the appearance of these remarkable polylogarithmic functions with a very special structure. And this sort of motivic content is starting to be seen in a really fascinating way in string tree amplitudes as well. Okay? So these are all things that have happened just in the last year. And there are so many things that I cannot possibly talk about all of them. So instead of reviewing everything, which would be impossible, I decided that what I would do is talk about one broad theme that, at least to my thinking, unifies a number of the threads of progress. And also tell you about some new work that I've been involved with along these lines. The theme has to do with, at the level of computation of amplitudes, a deeper and deeper appreciation for the power of locality and unitarity. And at a more conceptual level, a deeper understanding for new origins of locality and unitarity. So the entire rest of this talk is really going to be about locality and unitarity. Of course, all of physics is about locality and unitarity, but we're really going to focus on the sharp fingerprints of and the possible other origins of locality and unitarity in perturbative scattering amplitudes. So let me just start with some brief motivation for why we should be thinking about any of these things. I should have maybe said this as a disclaimer for the entire talk, but obviously I don't represent necessarily the typical view of workers in this subject. In fact, I may have a rather idiosyncratic attitudes about some things, but you should blame the organizers for inviting me. So this is my motivation for thinking about these things. And my motivation for thinking about gluon scattering amplitudes or gravity scattering amplitudes in perturbation theory actually has to do with these very deep questions we all know about. In this audience, I don't need to linger on them. That have to do with the fact that we know that space-time is doomed. We know the time part of space-time is doomed is very hard to understand. We don't know how to get a handle on that. And there are even reasons to suspect that there are places where at least quantum mechanics doesn't tell us what to do. It cries uncle. We don't know how to talk about, sensibly talk about quantum mechanics in these cosmological situations where we can't make a well-defined separation of the universe into an infinite system and a finite, into an infinite apparatus and a finite system that's being studied. So somehow we have to figure out how to replace space-time and perhaps even find some extension or a deeper understanding of what quantum mechanics is. And this seems like a very tall order. The most obvious way to work on this problem is to work on this problem and to think about exactly these questions. But there's another way of proceeding. This is not the first time we have encountered in physics having to give up seemingly hardwired principles in making big steps. We had to do this when we went from classical to quantum. And there is another way. There is another way that you can see what's coming next. If you have some hint for the principles that you have to lose, there's a way that you can see a hint for what's coming next by trying to reformulate the physics you have under your feet in as many different ways as you can, because one of those formulations might be best suited to making the transition to the next level. This is not something we talk about in the sort of philosophy of doing theoretical physics so much these days, but it's things like something that people like Dirac and Feynman went on and on and on about. They thought this was a very important thing. And the example, the transition from classical to quantum is a good example. F equals ma is manifestly deterministic, but people discovered other ways of thinking about classical physics via the principle of least action, which is not manifestly deterministic. At the time, it was mysterious why this other way of thinking about physics exists, but now we know why it exists. It exists because the world isn't deterministic. It's quantum mechanical, and the correspondence limit could not possibly have landed you on F equals ma. it had to land you on some way of talking about classical physics that was not manifestly deterministic. And that's why the principle of least action exists. And that's why if you discover the principle of least action, you've sort of gotten yourself 90% of the way there, because you're in the right frame of mind now. You've managed to do the really hard thing, which is to talk about exactly deterministic physics in a way that's not manifestly so. So the first stage is reformulation. Of course, the much harder part, but here at least you have a guide. Here you know what you're doing. Oops, why does this keep happening? Because whatever you do, you have to reproduce everything you did before. You're not changing anything. You're just trying to understand it in a new way, which must exist because the principle isn't really there. The much harder part is to figure out how to deform it and go from the principle of least action to the path integral. You know, historically, Hamilton was playing with things like this. So, you know, maybe given another 100 years, people would have discovered quantum mechanics even without experiment. But anyway, that's a strategy. This is a strategy that has worked before, or could have worked before. And so the strategy has two parts. First, reformulate standard quantum field theory, eviscerating completely locality and unitarity from our description of the physics, and see them emerge. See them come out as emergent phenomenon. That's the easy part. The hard part is then find a natural deformation, discover the path integral. Okay? And so anyway, this is the strategy, at least I've been pursuing for around 5 years. And I've been stuck on step 1. Step 1 divides into step 0, 1, 2, 3, 4, 5. And step 0 is to try to do this for n equals 4 super Yang-Mills on the planar limit. We're working with the wind to our back at 200 miles an hour. So if we can't do it for this theory, we're not going to, it's just probably not possible. The danger is that what we're doing is very special only for this theory, et cetera, et cetera. So as I'll say at the end, I suspect it's not so, but anyway, this is the strategy. No apologies. All right, so let's now talk about locality and unitarity and what they mean a little more sharply so that we can study these questions further. Obviously, locality and unitarity are hardwired into the usual quantum field theory formalism. The quantum and quantum field theory are making unitarity and locality manifest. And in perturbation theory, they're also hardwired as an obvious consequence of Feynman diagrams once we build all the usual gauge and diff redundancies into our description of the physics in order to make those things manifest. So, for example, at tree level, when we sum all tree diagrams, we get some complicated rational function. We don't know ahead of time what it looks like. But something that is obvious ahead of time is the locations of the poles of this rational function. The poles only occur when some sum of the subset of the external momenta goes on shell. Okay? So if someone hands you a rational function and it has a pole that looks like 1 over p squared q squared minus r squared t squared, you know they're lying to you. It's not local. It's not coming from summing Feynman diagrams. So locality tells you where the poles are, and unitarity tells you what the amplitude does on those poles. It has to factorize in this way. It's just a unitarity at tree level. All right, so that's what locality and unitarity is, and Feynman diagrams make it obvious. They make it totally obvious. Okay, now, so one thing you can do is now exploit locality and unitarity. Don't try to understand some second point of view for where it might come from. Just use the fact that you know the amplitude is local and unitary to try to directly determine it instead of summing Feynman diagrams. And that's the strategy at tree level of the BCFW recursion relations. So I'm repeating what I said before. When I draw this little del picture, I mean the first singularities of. So the first singularity of the tree amplitude factorizes into lower point tree amplitudes, and BCFW recursion, roughly speaking, uses Cauchy's theorem to reconstruct the amplitude from the knowledge of its poles, including its interesting poles at infinity. And there is this other way of writing it. So the amplitude itself is a sum of things that look just like amplitudes, except you pick 2 of the particles to be special and you deform their momenta. And in many cases, that deformation of the momenta can actually be thought of as a little loop picture like this, where these elementary 3-particle interactions have all particles sitting there on shell that carry out the deformation for you. Okay, so that's one thing you can do. You can use locality and unitarity to determine the amplitude. We can also ask another question. Are there other ways of representing, are there other ways of building objects that are guaranteed to be local and unitary, even at tree level? Okay? Feynman diagrams is one way. Are there other structures that we know that guarantee that the first singularities of the object make it split in 2? Okay? in a sense, physical words for what the theory are. The usual language we talk about are, from this point of view, just a way of making that fact obvious. And so we can ask, are there other ways of making it obvious? Well, there's a famous, old, classic way of making it obvious, albeit by adding new degrees of freedom, which is, of course, very closely related to the usual way, which is classic string theory. Okay? So here, too, we just look at a bunch of points on a Riemann sphere, and it's a beautiful fact that the naive singularities of this moduli space, where you bring the points close together instead of being ultraviolet, are conformally equivalent to a long, thin tube stretching between them. And so we get exactly that picture, that the singularities make it split in two. Okay? And actually, from this point of view, this is why twistor string theory exists. Okay? So of course, when Edward first showed us twistor string theory, it seems to come out completely out of the blue. But there is a way of at least understanding why something like twistor string theory should exist. It's because this picture, where you imagine integrating over all curves in twistor space, with the external points being supported on, for example, in this case, a conic in twistor space. This also gives you a way of making it manifest that the singularities make it split. So in this case, the singularities are, as you move the external data around, it's very easy to see that exactly when, in momentum space, you go to a factorization channel, in twistor space, it corresponds to this picture of the curve degenerating from a smooth conic into the product of two lines. Okay, so it's another way. So this is another representation of this basic fact that the singularities occur in this very special place. Now actually, in twistor space, it's not obvious that you get the correct factorization property. The location of the singularities is obvious. It's not obvious that it factorizes precisely correctly with the right kind of pole, which is where the magic and writing down good theories in twistor space comes from. Okay, and I think it still isn't clear what the rules are. If I write down a sort of a random theory that gives me amplitude supported on curves in twistor space, does it correspond to something in space-time? Probably not. On the other hand, at least I suspect that every sensible theory that we know and love has some representation in twistor space, because really, this is just a way of making these kind of factorization properties manifest. So for instance, and I think an interesting open question to me is there a twistor string theory for phi cube theory? We know now there's one for Yang-Mills, at least at tree level. There's one for gravity, as David explained. But is this really just, is this a way, sort of a universal way of making these factorization properties manifest, or does it only work for very special theories? Anyway, this at least gives some reason that it's not crazy that there is a structure like this in twistor space. And the way to think about it is just as yet another way and a more novel way, a less familiar way, of guaranteeing the existence of an object with the right kind of singularities that splits. Okay? All right. Now that was at tree level. Let's go to loop level. At loop level, the textbook definition of what locality and unitarity is has to do with the fact that beyond tree level, the amplitudes have branch cuts. And the location of the branch cuts, where they begin, tells you something about locality. And the structure of the discontinuities across the branch cuts tells you something about unitarity. Okay? So at the level of the final answer, that's what we are looking for. Now, people, of course, in the 1960s weren't even thinking about perturbation theory in doing this sort of thing. So they were trying to exploit it at the level of the final answer with all this incredible analytic structure. And somewhere I remember reading a statement by Weinberg, who said that he'd be very depressed if the analytic S-matrix program was the way to go, because to make progress with it, you would have to understand hopelessly advanced and complicated complex analysis in order to disentangle this crazy thicket of where the singularities are, what the discontinuities look like, and how to control all of them. Even in the very simplest cases of one loop amplitudes in perturbation theory, you have dilogarithms, polylogarithms in multi-loop order. So just controlling that thicket is complicated. And, well, in a sense, he was right. It took 30 or 40 years, but some of that technology is now available. The mathematicians have developed it. Okay? I'm not going to talk about it much here, but this entire field of symbology that was brought to light is really work of Sasha Goncharov for many, many years, that then found these beautiful applications in physics through this work in collaboration with these guys, gives us at least some of the tools we need for a limited class of functions, polylogarithms, which are not the most general kinds of things that show up in amplitudes, but they're general enough that they show up in lots of cases, where you can control the thicket of where all the singularities are, the discontinuities, and so on. And so the kind of classic method of trying to control the actual structure of the amplitudes directly, the final answer, in this way, is greatly aided by the existence of this technology. As is many other things, okay? And this is related to things Pedro talked about yesterday. We understand in the final answer properties of the operator product, expansion, collinear limits. In planar n equals 4 super Yang-Mills, we have integrability. We have hints from the Strassmannian structure that I'll talk a little bit more about. And these things together have combined into, at least for planar n equals 4 super Yang-Mills, a bootstrap program for the actual amplitude directly. Okay? All right, so that's using locality and unitarity as properties of the final answer in order to try to nail the amplitude. Now, we can actually take one step back before getting to the final answer. And something else we explain in textbooks is that locality and unitarity have an even simpler avatar. Not in the final answers, which have dilogarithms and discontinuities and things like that, but as a property of the cut structure of, loosely speaking, the integrand for the amplitudes. I'm putting the integrand in quotes because it's not obvious that such a thing as the integrand actually exists in a general theory. It's not obvious we can combine all Feynman diagrams together under one big integral sign. That's certainly not a gauge invariant thing to do in general and so on. But there's obviously a useful sense in which it's true, which has been used by many people. And anyway, so before we get to actually finishing the integrations, at the level of the integrand, unitarity is encoded in properties, again, of the singularities of rational functions, just like as it was at tree level. Okay? So, for instance, the classic double-cut textbook unitarity tells you that if you take the integrand and you put 2 of the intermediate lines on shell, then that rational function has to split, again, now in this way, with a guy on the left and a guy on the right, and you integrate over the on-shell phase space of everything in the middle. Okay? And generalizing this beyond classic unitarity cuts to arbitrary cuts was a big program that was pursued in these amazing works by Byrne, Dixon, Dunbar, and Kossauer in the 90s, going under the name of generalized unitarity. In planar theories, we can say even more. And in planar theories with at least 2 supersymmetries, we can say even more. Okay? First of all, in planar theories, there is a perfectly well-defined notion of the integrand. You can add everything up, and the word the makes sense. There is a canonical way of adding all the Feynman diagrams, and there is a canonical integrand. Okay? It's a consequence of planarity. And secondly, locality and unitarity now turn into a very transparent and sharp statement about the integrand, which is that the singularities of the L-loop amplitude, well, it has one piece, which is just the usual factorization, L1 and L2, L1 and L2 loops, where L1 and L2 add up to L. And the new piece that has to do with the loops is the other singularity you can have is where one internal guy goes on shell, and that should just be the so-called forward limit of the one lower loop amplitude. Okay? So that's it. So if someone hands you this big complicated rational function of the external momenta and the internal momenta, you can check if it's local and unitary by seeing if this is what its singularities look like. Now, this structure is very famous and very familiar. Okay? Joe is sitting there, so the first place I saw it was in his formulation of the exact Wilsonian renormalization group. There, the reason for this funny structure, again, the reason for the structure in all cases is here we're looking at the first singularity. So the first singularity can have one guy on shell, which is why you have that structure. It's similar to what happens in the exact Wilsonian renormalization group, where you have looking at exactly one mode, because you're just looking at the first order differential equation is the integrate one mode. This is, of course, it shows up all over the place elsewhere. Okay? So this is a deep and beautiful structure. And anyway, but in our case, it's a very sharp statement. I will make it a little more sharp in a second. Okay, but this now has backed us up to something a little more abstract than the actual S dagger S equals 1 at the end. This property of the underlying integrand is what's responsible for locality and unitarity. Where are the poles, and what do the residues on the poles look like? Once again, in these theories with enough supersymmetry, not just n equals 4 super Yang-Mills, certainly with n greater than or equal to 2, maybe even with n greater than or equal to 1. I can tell you what the technical complication is with n equals 0 later. But again, this control can be exploited. It can be exploited to calculate the integrand. And that's the philosophy of generalizing the BCFW recursion to all loop order. Okay? And it's really exactly the same thing. You know, we now have two kinds of singularities, and you just have the same sort of deformation of the external particles to recursively determine higher loop amplitudes from lower loop ones. All right, so now let me specialize even further to planar n equals 4 super Yang-Mills. And just to put a little more meat on the bones, I will fly through this, but just so everything is in principle there if you want to look at the slides later. Let's first talk about the actual functions. Anyway, I promised David that I would do lambdas and lambda tildes before his talk. So it's after your talk, but I'm doing them anyway. So first of all, we're dealing with the kinematics for massless particles. So we use these spinor helicity variables to talk about the external states. So we label them by these little two-dimensional vectors, lambda and lambda tilde. In gauge theory, we're dealing with color-stripped amplitudes. So we have an amplitude that's a function of lambdas and lambda tildes and the helicities of the external particles. We use an on-shell superspace to trivialize the action of Q or Q tilde, one or the other. So that means that we can label the states by this Grassmann coherent state, linear combination of the external helicities. So what we're left with is some function of lambda, lambda tilde, and these Grassmann variables, eta. And there's this variable called k hat here, which is that amplitude is a polynomial in the eta tildes. And the piece with 4k hat eta tildes in it is labeled this mnk hat. Physically, a k hat is a number of gluons with negative helicity in that sector of the amplitude. And this is something which is a beautiful cyclically invariant object in this planar limit. Another basic fact, the three particle amplitudes are nailed by Poincare symmetry. It's a simple standard argument I won't repeat, but the simplicity of special kinematics for three particles means that even for spin 17 million, it doesn't matter what, the three particle amplitudes are totally nailed by Poincare. Things start getting a little more interesting when we, so right now, we have trivialized the fact that the momenta are null, but it's still a quadratic constraint then that the momenta all add up to 0. So we can try to trivialize more and more, use less and less constrained external kinematics. And since the particles are ordered, we can draw this famous Wilson loop where we draw the momenta end to end on a four-dimensional piece of paper, and momentum conservation tells us that this is a closed polygon. Now, there's a completely standard way of representing this picture in the twistor space associated with this dual X space. Each one of these points is a line in each one of the points here is a line here, and the fact they're null separated with each other means that one line intersects the next. So that means we can fully reconstruct this picture of a null polygonal Wilson loop by just giving the points of intersection of these z's in twistor space. So these are these wonderful momentum twistor variables. And this is something extremely simple. It's just, it's a very simple algebraic translation between variables. There's no Fourier transformation or anything like that involved. Here's the explicit formula. But for our purposes, we just need to know that the external data is then specified just by giving four-dimensional vectors with SL4 acting on them. Okay? So instead of lambdas and lambda tildes, which are constrained to satisfy momentum conservation, you just hand me a bunch of unconstrained four-dimensional vectors up to a rescaling, so a bunch of points in P3. And they have some super variable partners. All right, so that's for the external data. What about the integrand? We want to talk about the singularities of this rational function, so let's talk about the integrand. Well, let's say we're looking at a one-loop diagram. Oops. Like this. Normally, we would write this as like d4L, L squared, L plus P2 squared, L plus P2 plus P3 squared, and so on. But when the diagrams are planar, it's natural to look at the dual diagram, and there's a more symmetrical and pretty way of doing this. Instead of calling this loop variable associated with the edge, we associate it with the face, just like we associate the external data. So that P1 is x2 minus x1, for example. So there's a loop variable associated with that face. And so what I called L before is just x minus x2. And for instance, this is, instead of d4L over L squared and so on, you just get this more symmetrical and nice thing. Okay? So the loop integration is integrating over points in this X space. And once again, it's natural, instead of thinking about points in X space, to think about lines in the corresponding twistor space. Okay, so the loop integration, so in the end, the amplitude, which was a function of n, k, and l, has some trivial pieces, momentum conservation and supermomentum conservation, and things just taking care of weights, times now something which is a function of n, k, and l, and is a function of a bunch of the external data, and L lines in P3. Okay? So you have some nice rational function there. Right. Now, in terms of, so now I won't go through it in detail, but we can just translate what locality and unitarity are supposed to mean in this language. And I just want to draw your attention to one thing. So locality is a statement about where the poles are. Now where the poles are, remember, is when some of the external P's goes on shell, which in this picture is just when two of these X's become null separated from each other, which means that the corresponding lines in twistor space intersect each other. Okay? So if I hand you some random rational function, it won't have the property that its only poles are when zi, zi plus 1, zj, and zj plus 1 all become coplanar, when those two lines intersect. Okay? But if those are the only poles, at least it's past the locality condition. So locality says these are the poles. This funny I plus 1, jj plus 1 structure is a fingerprint of locality. And unitarity tells you that it has to split. And splitting in this case turns into something very simple. There's a factor just telling you where these 4 points are on the plane, and it splits into a left piece and a right piece. Who is this internal point? Well, who else could it be? It's that point of intersection between these two lines in twistor space. Okay? So that's what locality means at tree level. And what does it mean at loop level, at locality and unitarity? Well, again, so this singularity happens when that line is going on shell, which means that x is becoming null separated from that x, which means that the line AB is intersecting the line II plus 1. So that's, again, where the pole is. And the residue on that pole needs to be given in terms of a certain simple residue of the one lower point integral as you take these points A and B and you move them towards that intersection point. Okay? So just so you see, it's some extremely concrete now, totally concrete property of this rational function that encodes locality and unitarity. And something else, of course, that we learned is that there are two sets of words, there are two sets of physics words that we can associate with exactly the same rational function. Okay? One set of physics words is gluon scattering amplitudes. The other set of physics words are the expectation value of this null polygonal Wilson loop. Okay? And they're giving us exactly the same function. In fact, how do we check in the end that these things are really the same? We check that these are both ways of guaranteeing exactly this singularity structure. Okay? So that singularity structure is universal. It's word and formulation independent. And the entire quantum field theory in one space or the dual space are just ways of making it obvious on both ends. Okay? So this is already interesting. So we're learning yet another way of representing this kind of singularity structure. Had you asked me, of course I'm not very bright, but had you asked me, how do you engineer that you find some object that has a sort of singularity? Say, beats me, other than if there's something is going on shell propagating in space-time, it's a gluon, right? You come along later and say, no, there's a Wilson loop, and it's because two of the cusps of the Wilson loops are getting null separate from each other. Oh, wow, that's another way of doing it. Isn't that interesting, right? So those are different words for exactly the same invariant information. All right. So this now brings me to at least the thing that's been the driving force behind my own work over the past 4 or 5 years, which is associated with the motivations I mentioned, which is that, and sorry, I should have said here too, these two sets of physics words make different symmetries manifest. One makes conformal invariance manifest, the other makes dual conformal invariance manifest. They combine into this infinite dimensional Yangian symmetry. That's the real symmetry of the problem, that the usual local unitary descriptions totally obscure, right? You can only see a tiny part of them by making a commitment to one or the other. And so that's a clue, amongst other things, to say, is there some other way of formulating the physics? Is there a different question to which the amplitude is the answer? Okay? Or the Wilson loop is the answer? Is there a different question that has that as the answer? This formulation P, which we're looking for a long time, should be some way of talking about the physics that also makes this obvious, but without gluons going on shell or things in space-time becoming null separated from each other. And we should then hopefully see that locality and unitarity emerge. They're not built in to the picture, they emerge. And amongst other things, the infinite symmetry should be obvious. Other properties should be obvious, okay? All right. So there's been a path towards trying to uncover this structure, and at various junctures in this path I've given talks at strings meetings. So on the very last meeting last year, what I talked about was the culmination of about 2 years of work with my collaborators and some mathematicians that got sort of 80% of the way there. I'll tell you what it was missing, and the rest of the talk some of the rest of the talk will tell you what the more complete story is now. But an important ingredient in what I talked about last year was this idea of on-shell diagrams, that we start thinking about scattering amplitudes by never mentioning the word virtual particle, and instead just taking these elementary building block 3-particle amplitudes, these black and white vertices, gluing them together on shell in every possible way, and then starting to understand that these objects have a life of their own. Okay? They have a beautiful structure and life of their own, and amongst other things, not only are they of interest by themselves, but the actual amplitudes are built and can be represented by sums over these on-shell diagrams. Okay? And these on-shell diagrams, on the one hand, which is a natural thing to do, gluing together elementary interactions, turn out to be related to this beautiful structure in algebraic geometry that a number of our mathematician friends had accidentally run into in the last 5 years or so, known as the positive Grassmannian. And I want to very briefly remind you about that, because we'll be generalizing it greatly momentarily. So let's forget about physics for a second. Let's just look at k by n matrices modulo GLK, which is a way of representing k-planes in n dimensions. In fact, I'll think of it as just k n-dimensional vectors modulo GLK. And we're going to imagine they're all real. Not only are they real, but all the minors of these matrices are positive. This generalizes the notion of a simplex, just a triangle, as we'll talk about in a bit, from projective space into the Grassmannian. Okay, so all the minors are positive. We have to pick some ordering for the external particles. That's good. We have a cyclic ordering for the external particles. So given the ordering, you build this k by n matrix mod GLK, and you look at that part of the space that has all the minors positive. That's it. Studying what that space looks like is a whole interesting science. Okay? And it's not at first clear how it's related to amplitudes, but that's what I talked about last year. Let me just give you a little bit of intuition for what positivity means. So let's actually do it not for the simplest case of G2n, but G3n, which is a little easier to visualize. So we have n 3-dimensional vectors. Since everything is projective, we can just think of them as n points in Euclidean space, projectively, or n points in P2. And if I hand you n random points in P2, all the minors won't be positive. So what would they have to look like for all the minors to be positive? The answer is they would have to form a convex polygon. Okay? So positivity is the same as convexity in this case. Now, convexity is not so obvious how to generalize to higher spaces, but this statement about minors does generalize to higher spaces. So it's a generalization of the notion of convexity. Okay? All right. And anyway, there's a long story which allows you to understand what the space looks like. It ends up really being essentially combinatorial, as I described last year. And at least this is a logical connection between all of these different subjects that don't at first seem related to each other. But on the one hand, we have this picture of convex polygons, or the positive Grassmannian, which is its generalization. It is completely determined. A particular configuration that satisfies it turns out to be completely determined by a certain permutation. Okay? So the backbone is combinatorial. And it can also be represented by these diagrams with black and white vertices, which are exactly the on-shell diagrams that we talked about, and actually be directly computed in that way. In fact, if you begin with these diagrams and you actually try to calculate them in an efficient way, you're forced to discover this structure. And the way you read off the associated permutation is to walk into the graph and make a right turn at a black vertex and a left turn at a white vertex, and that tells you what the permutation is. Okay, okay, so and amongst other things, this way of organizing the amplitude, no virtual particles, everything on shell, makes the infinite dimensional symmetry totally manifest. In fact, it's so obvious you barely notice it, but the second you think to ask about it, it is obviously there. It's in fact positive diffeomorphisms that just leave this positive space invariant to just give you this infinite dimensional Yangian symmetry. Okay, so that was the story from last year. But the complaint at the end of my talk, at the end of all these papers, has been exactly the same year after year, very frustrating, which is that there's been a beautiful story for the building blocks of the amplitude, these individual on-shell diagrams. But why do we have to combine them together in this very particular way, as dictated, for example, by BCFW recursion, to get the actual amplitude? Why do we add them up in that way? Of course, the answer is to make the result local and unitary. Right? So if your goal is to exploit locality and unitarity, we're done. Right? But somehow the fact that exploiting it writes the answer in terms of these objects with such a nice life of their own begs the question, is this the answer to some other question? Is this the answer to some other natural question where we've never heard about locality and unitarity or BCFW recursion or any of that, and we see that this is a nice collection of objects to add together? The fact that we were missing this picture was, as I said, was very frustrating. One of many indications of this, it's a funny one to say, but it indicates part of the problem, is that while we had infinite fun with our math friends understanding, and they were very excited about understanding the building blocks, I could not get them remotely excited about adding everything up to get the whole amplitude. They had no idea why we were doing that. You know, it did not occur to them as anything natural to do. Why the hell would they do that? Okay. All right. So that's now what I want to tell you about. So that's what we now have the answer to. But before getting there, I want to just give you one example. The simplest example of this is the simplest non-trivial tree amplitudes, these NMHV trees. This is a very simple example because the building blocks that you get from the Grassmannian, there's essentially one object. You don't need to follow any of the details, but there's one object labeled by five external data, 1, 2, 3, 4, 5. This is its Grassmannian representation. This is it as a concrete function. Okay, so we have these basic so-called R invariants. There's only one thing in this case. In general, there's many more building blocks. In this case, there's just one building block. And what BCFW instructs you to do is add up this funny combination of them. The sum over 1, II plus 1, JJ plus 1. Okay? Now, why? Why are you doing this? Now, the II plus 1, JJ plus 1 looks good. That looks like the sort of local poles we were talking about before, although no one told you about locality. Why would you care about II plus 1, JJ plus 1? But you see other funny things. There's the 1 sitting here. That's not cyclically invariant. So there's some identity that tells you that if you replace 1 by 2, you get the same answer. Okay? And each term has many, many poles that aren't local. And they all cancel magically in the sum. Right? So anyway, the question is, why this combination? Now, for a number of years, we've had also a vague fantasy. In some very simple cases, this fantasy was concretely realized, but we didn't know how to do it in general. And the fantasy, or the vague fantasy, because it's vague, I can say it maximally vaguely, is that the amplitude is somehow the volume of some region in some space. And there's just many different triangulations of this volume. No one preferred over the other, but the actual object is this volume. So that has a lot of the qualitative features of the things that we've seen. Many different representations, all giving you the same answer. And the hope was that if we understood what this volume was and what the region was, that we could see where locality and unitarity came from. Okay. And as I said, that's now what we know how to do, so I want to spend my last 20 minutes or so telling you about how it works. So this is work that should appear sometime soon with my student Yaroslav Turinka. All right. So in fact, what we're going to do is, as we'll see, there are two structures. There's the one that we've been studying for a long time that I talked about last year, the positive Grassmannian, which you can think of as a generalization of a triangle, right? So let's first talk about that. So let's start with the venerable triangle. So here's a triangle. And let's say I want to talk about the inside of that triangle, the points that are inside of that triangle. Well, the most convenient way of doing this is to use projective coordinates. And the inside of that triangle are all the points of the form C1, Z1 plus up to C3, Z3, where all the C's are positive. It's like the center of mass, where all the masses are positive. Okay? So there you go. The inside of a triangle is associated with a triplet of numbers, positive numbers modulo GL1. That's the positive Grassmannian for the trivial case of G13. We can generalize this to an n-dimensional simplex, that's G1n, and the generalization to the Grassmannian, where instead of numbers, they're k-dimensional vectors, is the positive Grassmannian. So that's the sense in which the positive Grassmannian is a generalization of the triangle. So the things that we've been playing with all this time are like building blocks. They're like triangles. Now the question is, what are these building blocks gluing into? Well, let's go back to our simple two-dimensional space and think about the other generalization of a triangle, which is to polygon, right? So now imagine we have n points, 4 points even, and I want to talk about the inside of a polygon. Already life is more interesting, because if I just say the points are z1, 2, 3, 4, and their points are totally random, it's not obvious what I mean by the inside, right? They might look like some crazy thing, and the inside isn't well defined. For the inside to be well defined, some constraint needs to be satisfied on the external data. They have to be convex. But once they're convex, we can talk about the inside. Okay? So now, remember, convexity can now be stated as this way, that if I look at now the external data as a bunch, in this case, n three-dimensional vectors, if there are points in P2, then all the minors, the ordered minors of the external data should be positive. That's one constraint to make them convex. Once it's convex, the interior of the polygon is a weighted sum of all of them with positive coefficients. So the inside of a polygon is an interesting marriage of two positivities. Positive external data weighted together in a positive way. Okay? As we'll see, we're just going to generalize that idea, and generalizing that idea is scattering amplitudes in n equals 4 super Yang-Mills. Okay? Let me say one more thing about it. So this is a two-dimensional space. The space of all C's is n minus 1 dimensional, so that's a highly redundant covering of the inside of the polygon, right? So I can build the inside of the polygon by two-dimensional cells of positive G1n. And the two-dimensional cells are just all the little triangles that I can have. So the stupid thing I can do is take the union of all of them. I can do more interesting things by triangulating the space in a way that they don't cover each other. Okay? And so here's one. There's many, but here's one triangulation. 1, 2, 3 plus 1, 3, 4 plus 1, 4, 5. The sum over I, 1 I plus 1. A final thing is that now a natural thing that I can do is ask for the area of that region. Area has units and is not a very nice projective idea. But there's a very closely sort of dual notion to area. If I hand you this convex polygon, I can talk about the area, or I can talk about something else. I can talk about a two-form in P2. I can talk about a two-form in P2 that has the property that it has logarithmic singularities on the boundary of the triangle. Okay? That's very closely related to the notion of area. In fact, in projective space, they're almost the same. They are the same, essentially. One is proportional to the other. They both have the same additive properties. If you have two regions that share a common boundary, the forms add the same way the volumes add, and so on. And also, it's very easy to find such a form if you triangulate the space. For example, here's what it is in y space written invariantly. Here's what it is in particular positive coordinates, where the points inside are, again, the positive combination of the external data. Then it's just the d logs, wedging together the d logs of all the positive coordinates. Okay? And for instance, if I want to know what is this area for a general polygon, if I triangulate it, I just add these d log measures for each one of the triangular pieces. Okay? I also want to stress that this hands me in the end a completely complex form. Doesn't care about the external data being positive, doesn't care about any of that. In fact, you could say it another way. There is a nice complex form out there that has the property that if the external data was positive, that form would have logarithmic singularities on the boundary of that region. But it's a complex statement. Okay? All right. So let's generalize this. Let's generalize the inside of a polygon. The first generalization is to say that the z's are higher dimensional. Instead of being points in P2, P3, P4, they're anything you like. You can quickly show yourself, you can quickly see that this thing is only nice and cyclically invariant. So this I, instead of running from 1 to 3, is going to run from 1 to m in general. You can quickly show that m should be even. And so we're just generalizing by saying that, again, the external data is in the positive part of G1 plus mn, and the coefficients are in the positive part of G1n. The polygon was the simplest case, m equals 2, so the first new case is m equals 4. Now, this is a more interesting space. It's harder to visualize. It's a 4-dimensional space. And I won't go through this in detail, but just to give a flavor of the argument, It's hard to visualize, but we can explore, for example, what do the boundaries of this space look like? Right? To find what the boundaries look like, all I have to do is take my point y, which is on the inside of the space, and I want to see, does it lie on some general plane made out of the external data, A, B, C, D? Every time there's a bracket here, I'm just contracting everything with the epsilon symbol. Okay? So if that quantity has a uniform sign, then it's a boundary. If it can switch signs from one side to the other, then it's in the middle of the space somewhere. Okay? Well, it's trivial to figure this out. So the y's are a linear combination of the external z's. And remember, all of these, the c's are positive, and if the z's are ordered in increasing order, those minors are positive as well. So there's a chance for some of these things to be positive. But it's very simple to see that if these are completely general indices, A, B, C, D are totally general, they're not. Some of the terms are positive, some of them are negative. But in a very special configuration, they're all positive. That special configuration is when A, B, C, D is I plus 1, J plus 1. So remember I told you there's something special about I plus 1, J plus 1. Those are where the poles are. Right? Those are where the poles in the amplitude are. That's locality. Here we see in this space, the boundaries of the space are the planes I plus 1, J plus 1. Not surprisingly, we'll see that the singularities of the amplitude in the picture I'm going to tell you maps to the boundaries of the space, going to the boundaries of the space. So already we discover locality from positivity. Okay? The fact that I plus 1, J plus 1 is special is a consequence of positivity. In fact, you can take the space and triangulate it, just like we triangulated the polygon. And its triangulation is exactly this expression. 1 I plus 1, J plus 1 is the simplest thing. That's exactly what I showed you as the NMHV tree amplitude a moment ago. So before we wanted to know, why the heck are we adding these objects up together in this way? Now we know. They're gluing together into the volume of this nice space. Okay? And that space is just the generalization of a polygon, the straight generalization of a polygon into a higher projective space. As we see, locality follows from positivity in this case. Now, there's a totally obvious generalization, one further generalization. Just like we generalize a triangle to the positive Grassmannian, instead of having one y, which is on the inside, we can have ky's that are on the inside, and mod out by glk. So this is the basic object. So y is a positive combination of positive external data. So the z's are 4 plus k dimensional vectors, and the c's are positive now in the usual sense of the positive Grassmannian. And so this is now defining some analog of the polygon, not in projective space now, but in GK plus 4, or GK plus m in general, but we care about the case where in physics where, it's, where m is 4. Okay? So it's just a generalization of the polygon into GK plus 4. Now, something that might bother you is, where's the external data here? Remember, I told you the external data is supposed to be bosonically 4-dimensional vectors. This object is 4 plus k dimensional. Well, again, I won't have time to explain any of this in detail, but part of the story involves a new treatment of supersymmetry. So we don't think about supersymmetry in the usual way. We don't think about supergeometry in terms of equal numbers of odd and even variables. In fact, instead of doing that, everything is completely bosonic. But all the information about the Grassmann variables is packaged instead of having a vector in P3/4, we have a bosonic object in P3 plus k, and all the extra information is packaged in the lower components of that matrix. That perfectly goes along with the fact that our object lives in GKK plus 4, because if you specify a given plane, a given point in GKK plus 4, that gives a natural separation of GKK plus 4 into that k plane and its complementary 4 plane. The bosonic data lives in that complementary 4 plane. The rest of the data lives inside the GKK plus 4 part. Thanks. All right, so that's so no supergeometry, but bosonic geometry. All right, so having done all of this, the amplitude is just the volume of this region. The tree amplitude is the volume of this region. Okay, and BCFW can be seen to be one triangulation, or more precisely, one cell decomposition of this space. But the thing that I find exciting is that without computing the whole full amplitude, we can discover that it's unitary. And in fact, you discover that we know where the boundaries are. The boundaries are II plus 1, JJ plus 1. So you go to the boundary, and 5 lines of algebra playing with determinants and positivity shows that the boundary splits. splits exactly the way the amplitude makes it split. It's a property of positivity that the only way you can make a matrix with positive minors whose top row looks like that is for the rest of it to split, which gives you precisely the picture that we need for unitarity from positivity. That was a picture for trees. What about loops? Well, remember, the loop integration variables are, if we just go back to space-time, to the usual picture for a second, we're supposed to have this information about lines in P3. Okay, and those are the loop variables. So what could the story possibly be? Well, let's say we're just even doing k equals 0, the MHV amplitudes. The only thing it could possibly be is that each one of these lines itself is a positive combination of the positive external data. Okay? So at one loop, each line is living in the positive part. At many loops, they have to interact with each other somehow. And the way they interact with each other is just say that all the minors are positive. Okay? So each one of these lines is a positive combination of positive data with the additional constraint that all of them are mutually positive with respect to each other. That's the only natural thing from this picture. And actually, even if you didn't think about this, you would discover it if you asked the following question. If you start with the structure that we had already, and we asked, what if we wanted to hide particles? We didn't want to look at a bunch, some collection of the particles. We literally wanted to ignore them. If you take these large matrices and you literally ignore many of the columns, then what you get on the remaining columns are positivity constraints of exactly the sort that we were talking about. In other words, the positivity of the minors of these big matrices imply exactly the kinds of positivities on these little ones that were the things that were the only natural thing that we could do anyway. Okay? Let me just tell you what the story is in the simplest case of 4 particles. Okay? 4 particle MHV amplitudes, all loop orders. You just have to solve the following math problem. Okay? This is the space. Okay? There's some concrete coordinates. But just so you see how simple these things are. So each loop variable is 4 variables, right? Each loop is 4 variables. They're grouped into 2 two-dimensional vectors A and B, both of which are in the positive quadrant. So X, Y, W, Z are all positive. And the mutual interaction condition is just that AI minus AJ dot BI minus BJ is negative. That's it. Okay? You just have to understand that space, triangulate that space, find coordinates for that space, solve that space. You solve that space, we're done with the 4-particle integrand to all loop orders. And it's, again, it's clear it's a problem you can give to a junior high school student. In fact, I have given it to junior high school students. They haven't helped me much with it. So this is a slightly harder problem than it seems at first. We've been trying to solve it for about a month and a half now. But I stress, I mean, it seems like the sort of thing that maybe just needs 1 or 2 good ideas, and then you crack the amplitudes to all loops. Okay? Now, but again, something that you just see, even without solving the problem. A consequence of these various positivities is, even without fully solving it, you can see that if you cut 2 of the internal lines, it splits exactly like it's supposed to by unitarity. So unitarity follows from positivity. Okay, anyway, and I don't have time to explain this in detail, but this is the whole picture. The whole picture is that the full amplitude for any k and n lives in the following space. It's gk k plus 4, so it's k planes in k plus 4 dimensions. And in the complement of the k plane, which is a 4-dimensional space, there are L lines, and everything is a positive sum of external data. That's it. And the volume of that space is the amplitude, and you can show from positivity that it's local and unitary. So that actually follows from positivity. All right. So in this picture, all the symmetries are manifest. Determining the integrand reduces to triangulating this space. At tree level, it's clear that BCFW is somehow a very canonical and nice way of doing this triangulation. At loop level, it is not. At loop level, it's a way of triangulating it, but there are clearly better ways of triangulating that we haven't discovered yet. It's a very simple mathematical structure. As I said, it just generalizes the notion of a polygon into the Grassmannian, together with the idea of hiding things to give you loops. But it gives a complete and autonomous definition of all scattering amplitudes in planar n equals 4 super Yang-Mills, which is clearly totally free of the usual QFT language. There's no Feynman diagrams, obviously, but not even unshelled diagrams, recursion relations, nothing. Okay? The amplitudes are the answer to this question in a way that makes all the symmetries manifest. The role of twistor space in this picture can be seen as really purely kinematical. Okay? They're the best possible variables with which to talk about the external data, but what gives the object life, what turns it into an amplitude is just essentially this one extra idea of positivity. And I should say this has all been about the form that we integrate to get the answer, but there's recently been some very interesting indication for the important role of positivity in terms of the external data for the final results, which is this very interesting work by these guys that showed that the final answers post-integration are written in terms of very special combinations of the external data that can be recognized as so-called cluster variables, which are a fingerprint of the positive Grassmannian for the external data. All right, so let me just end. So we now have a very baby example, but an example nonetheless of emergent locality and unitarity. Unlike conventional formulations of quantum field theory, they don't fight each other. That's, I think, one of the things I find most interesting. And instead, they emerge together. They emerge together at the same time from the same principle. I should say that this structure is totally unknown to the mathematicians. So that, the previous structure of the positive Grassmannian was known to them for a little while, so it was lots of fun interacting. This is unknown to them, so it'll be even more fun interacting with them. And again, while before I couldn't possibly get them excited about summing BCFW terms, now there's 3 or 4 of them who are busily working on trying to triangulate this space. Okay? I should also say there's still something missing. We still have something missing in our understanding because it's still loop order by loop order. The space changes. As I go to 10 loops, I have the space GKK plus 4 with 10 lines in this 4-dimensional dual to the K-plane. We would like to have a non-perturbative definition where we can in principle sum everything up. And what's missing, I keep telling you that the amplitude is a volume, but so far it's a rather abstract kind of volume in the sense of this form with logarithmic singularities on the boundary of the space. We're looking for, and we're sure this exists, it's going to be something rich, it's not a trivial notion of volume, but there's an actual volume. There's some sort of integral representation for these forms that we're looking for. And I suspect that this is the missing piece for making contact between the work that we've been doing at the level of the Integrand for many years and all this fantastic work that's been going on at the level of the final answer, at strong coupling, ADS-CFD integrability, and so on. All right, so let me just end with 2 general comments and speculations. First, this whole business is an example of something that's not dualities. Okay? We've got a lot of mileage out of dualities. Dualities are incredible things, but dualities have given us equivalences between existing physical pictures that we've known and loved for a long time. 2 different gauge theories, gauge theory and gravity, right? Those sets of words, those ways of integrating in redundant degrees of freedom to describe physical observables existed for 80 years, and then we found equivalences between them. This story is not that. We're finding new ways of representing these things. They're not, they're not things that were sitting there before. And I gave you 3 examples of sort of deeper origins of locality and unitarity. Classic strings was a very familiar one. Of course, it involves adding extra degrees of freedom. Twistor strings is a new one, this new way of making locality manifest. And maybe it works at loop order. Maybe it'll also work for in general. We still don't know the story at loops. These Grassmannian representations are, in a sense, the most abstract of them so far. They don't have any obvious space-time heritage. But they work for these planar theories. We don't know if they work in general. I suspect there must be many more of these things, and that we should learn some deeper origin of them and perhaps a more unified understanding for where they come from. I strongly suspect that there is some story like this for gravity as well. Yang-Mills beyond the planar limit gravity, and this is a whole other talk to give, but I should say that even in the planar limit, there's lots of unexplained magic. There are relations between the amplitudes in different orderings that are actually there that are totally invisible to us. We have no idea where they come from. Especially these remarkable Bern-Carrasco-Johansson color kinematic duality relations. These are things that are there. We have no idea where they come from. There are even things that sit there in the planar limit. So there has to be something that glues these objects together in a bigger setting that makes it work. Okay. And the final, most provocative thing I will say, probably most likely to be wrong, but I somehow feel that it's likely true, is that at the concluding talks of so many of these string meetings for the last decade, people keep talking about needing to understand emergent spacetime, emergent spacetime, emergent spacetime. I suspect that it's not just emergent spacetime, but that we have to see spacetime and quantum mechanics both together emerge in a way that the two of them are inextricably linked to each other. Okay? And there are lots of qualitative general reasons you might suspect something like that is true, but in our very baby example, that's exactly what is happening. Okay? So we don't have the two of them together. There's this other structure, and locality and unitarity emerge together. I suspect that's going to be general. Thank you.
So we will have about a couple of questions.
I just have a remedial question about this thing you've emphasized now a couple times, that they emerge together. I mean, obviously in quantum mechanics you can have unitary evolution much more easily than you can have local physics. You can have a unitary evolution that's blatantly non-local. So why should they always emerge together?
Oh, I'm not talking about general quantum mechanical. I'm talking about the real world, right? I mean, our actual world has relativity. And quantum mechanics. And what I'm saying is that the fact that there is relativity and quantum mechanics, from the usual point of view, is exactly along the lines of what you're saying. There's quantum mechanics, there's relativity, then you can force the two of them to play. And if you force the two of them to play, it's the entire structure of quantum field theory that we're familiar with. We have to introduce all this redundancy, blah, 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 right? That's what you're saying is exactly the conventional picture. They don't have to be. One doesn't have to exist. They could exist independently. We have to do a lot of extra work to make them play together. What I'm suggesting is that there are other pictures where you don't do extra work. They actually naturally come out together in a way that's inextricably linked to each other. Right. Yeah.
Very nice. But in these black hole problems, for example, that you mentioned, there's unitarity, but maybe not ordinary locality. So. World, we don't know.
Sure, I agree, and incidentally, I mean, of course, as I said in the strategy, part 0 is reformulation of totally standard local unitary, completely ordinary physics. The hope is that look, there's probably some other structure out there we still don't know. It probably involves new sorts of mathematical things that we haven't seen, new sorts of engines that make it work. The question is, how do we find what those pieces are, right? And I don't know this is the way to go, but it's a way to go, to try to force ourselves to talk about local and unitary physics with our hands behind our back without using them. As we see, we can do it in some cases, and maybe it's telling us something about the kinds of structures that are going to show up in the hoped for precise theory that we're ultimately after.
Last question? Yeah, up there.
So it seems to me that everything you said about locality and unitarity applies equally to gravity. So are you saying that there is a similar representation for, let's say, Hodge's formulae?
I very much hope so. I mean, let me just say I tried to say one circumstantial, at least optimism in that direction. But let me mention another. One of the driving forces behind all of this thinking has been, even in gauge theory, that we found these beautiful BCFW representations of the amplitudes in terms of these basic building blocks. Those building blocks end up being very nice. You discovered later they show all the symmetries of the theory and so on and so forth. But you have to understand, why are two ways of doing BCFW? Why do they give you the same answer? Well, there have to be crazy identities that are satisfied between these objects. Where do those identities come from? And you ask these questions, and you eventually go through a long, long chain, and you see the reason is that there are triangles. They're gluing together to build a big object. Okay, so the underlying thing we could see even at the very beginning in the explicit expressions, that there are tons of different representations all giving the same answer, did have a deeper geometric origin ultimately. Exactly the same is true in gravity. Even more, crazily more, many identities have to be satisfied between these objects. They have a very combinatorial feel to them. They have the whole time. For Yang-Mills, that combinatorial feel has been, turned into this structure. I strongly suspect the same thing is true in gravity. I very strongly suspect the same thing is true in gravity.
Okay, let's thank we are behind the schedule. Let's thank the speaker.